The science begins underground. All volcanic eruptions start deep beneath the Earth's crust, about 30 to 100 kilometers below the surface. Intense heat from the mantle melts rock into magma, a mixture of molten minerals, gases, and crystals. This magma doesn't stay still. Because it's less dense than the surrounding solid rock, it slowly rises toward the surface, collecting in underground chambers called magma reservoirs. The pressure builds as more magma enters these chambers. Think of it like shaking a bottle of soda. You can't see the gas pressure inside, but once the cap opens, all that trapped energy bursts out violently. The role of gas pressure. The real key to how explosive an eruption becomes is gas pressure. Magma isn't just liquid rock. It's packed with dissolved gases like water vapor, carbon dioxide, and sulfur dioxide. As magma rises, the pressure around it decreases, and these gases start to expand and form bubbles. If magma is thick and sticky, which we'll get to next, these gases can't escape easily. The bubbles keep growing, forcing the magma apart until the pressure becomes unbearable. Eventually, the rock above the magma chamber cracks open, releasing all that pressure in a catastrophic explosion. This is why gas-rich magma creates the most violent eruptions, comparable to a shaken soda bottle finally bursting open. Viscosity, the magma's personality. One of the biggest factors that determines how explosive a volcano will be is magma viscosity, how thick or fluid the molten rock is. Magma comes in different types depending on its chemical makeup. Basaltic magma is runny and low in silica, so gases escape easily. That's why Hawaiian volcanoes like Mauna Loa have gentle, flowing lava fountains rather than huge explosions. Rhyolitic or andesitic magma, on the other hand, is rich in silica and extremely viscous. The gases can't escape, so pressure builds up until it blows the top off the mountain. Mount St. Helens in 1980 and Mount Pinatubo in 1991 are perfect examples. Both were silica-rich volcanoes with trapped gas pressure, leading to massive, explosive eruptions. The role of plate tectonics. Volcanoes exist because the Earth's crust is constantly moving. Most explosive volcanoes are found along subduction zones, where one tectonic plate slides beneath another. As the oceanic plate sinks, it melts due to heat and pressure, creating magma that rises to the surface. These magmas tend to be thicker and gas-rich, which explains why volcanic arcs like Japan, Indonesia, and the Andes are home to some of the world's most violent eruptions. In contrast, volcanoes at mid-ocean ridges or hot spots, like Iceland or Hawaii, produce more fluid lava and are usually less explosive. The build-up, pressure, and magma chamber expansion. Before an eruption, a volcano gives several warning signs. The magma chamber begins to expand as it fills with molten rock and gases. The surrounding rocks crack and shift, causing small earthquakes called volcanic tremors. Gas emissions from vents increase, and the ground around the volcano often swells. Scientists use these signs to predict eruptions, but the exact moment when the pressure threshold will break is still difficult to pinpoint. When that pressure finally exceeds the strength of the overlying rock, the eruption begins, sometimes with an ear-splitting explosion heard hundreds of kilometers away. Pyroclastic eruptions, the most explosive kind. When gas-rich magma violently explodes, it sends a deadly mix of hot gas, ash, and rock fragments racing down the volcano's slopes at speeds over 100 kilometers per hour. These are called pyroclastic flows, and they're among the most dangerous phenomena on Earth. They can flatten forests, bury cities, and kill everything in their path. In 1902, the eruption of Mount Pelée on the Caribbean island of Martinique destroyed the city of Saint-Pierre in minutes, killing more than 28,000 people. The explosion was so powerful that it vaporized water, shattered rock, and hurled molten fragments miles into the air. Volcanic Explosivity Index, VEI. To measure how explosive a volcanic eruption is, scientists use the Volcanic Explosivity Index, or VEI. It ranges from 0, non-explosive, to 8, megacolossal. For context, Mount St. Helens, 1980, scored VEI 5. Krakatoa, 1883, scored VEI 6. It produced explosions heard over 3,000 miles away. Tambora 1815 scored VEI 7, the largest eruption in recorded history, releasing more than 100 cubic kilometers of ash and gas. Tambora's eruption was so massive it caused the global temperature to drop by nearly 1 degree Celsius, leading to the year without a summer in 1816. Water's role in explosive eruptions. Water makes eruptions far more dangerous. When magma comes into contact with groundwater or the ocean, it instantly flashes to steam, expanding violently. This process is known as a phreatomagmatic explosion. The rapid conversion of water to steam can multiply the power of an eruption, turning what might have been a mild event into a devastating blast. This was seen during the 1963 eruption of Mount Agung in Bali and again in Iceland's 2010 Eyjafjallajökull eruption, which disrupted global air travel for weeks. Ash clouds and atmospheric effects. Explosive eruptions launch vast amounts of ash and gas into the stratosphere, sometimes over 30 kilometers high. Volcanic ash isn't like fireplace soot. It's made of tiny, razor-sharp glass particles that can destroy aircraft engines and collapse buildings. Sulfur dioxide released during eruptions combines with water vapor to form aerosols that reflect sunlight, cooling the planet. For instance, Mount Pinatubo's 1991 eruption lowered global temperatures by about 0.5 degrees Celsius for nearly 2 years. These particles eventually settle, but large eruptions can temporarily shift global weather patterns. The chain reaction of destruction. The explosion is only the beginning. Eruptions can trigger secondary disasters like lahars, volcanic mudflows created when ash mixes with rain or melted snow, burying towns in thick sludge. Tsunamis. Underwater or coastal eruptions can displace massive amounts of water, generating deadly waves. Acid rain. Volcanic gases like sulfur dioxide and hydrochloric acid mix with moisture, damaging crops and contaminating water supplies. The ripple effects of a single eruption can last years and reach across continents. The biggest explosions in history. Some eruptions are so powerful they're seared in human history. Mount Vesuvius, 7980, buried the Roman cities of Pompeii and Herculaneum under thick ash and pumice. Krakatoa, 1883, produced one of the loudest sounds ever recorded and sent tsunamis up to 40 meters high. Mount Tambora, 1815, killed over 70,000 people and darkened skies across the world. Mount Pinatubo, 1991, released 20 million tons of sulfur dioxide into the stratosphere, cooling the Earth for years. Each of these eruptions changed the climate, geography, and even human history. Could it happen again? Supervolcanoes, yes, and on an even bigger scale. Supervolcanoes like Yellowstone in the US, Toba in Indonesia, and Taupo in New Zealand have the potential to produce eruptions thousands of times more powerful than Mount St. Helens. If Yellowstone were to erupt today, it could release over 1,000 cubic kilometers of ash, covering much of North America and blocking sunlight worldwide. While scientists say such eruptions are extremely rare, occurring roughly once every 100,000 years, the potential impact is almost beyond imagination. Modern monitoring and early warnings. Today, volcano monitoring has improved dramatically. Scientists use satellite imagery, seismographs, GPS ground sensors, and gas detectors to track volcanic activity. Agencies like the U.S. Geological Survey, USGS, and Smithsonian Global Volcanism Program maintain global databases to predict and respond to eruptions. Although predicting the exact timing is still hard, many lives have been saved through early evacuations, like before the 1991 Pinatubo eruption, when scientists' warnings helped evacuate over 60,000 people. The human and environmental impact. Explosive eruptions can destroy communities, but they also shake the planet in powerful ways. They create fertile soils rich in minerals, form new islands, and even contribute to the carbon cycle that stabilizes the atmosphere. Civilizations have always lived near volcanoes despite the danger, drawn by the benefits of fertile land and geothermal energy. It's a reminder that volcanoes are both creators and destroyers, forces of renewal as much as devastation.